Okay. All right, guys. I welcome you all to this week's interactive session of the course Fundamentals of Conduction and Radiation. And if you guys remember, in the last week, we started off with radiation heat transfer. We finished conduction in the week before, and then we started with radiation heat transfer. And if you if we have a quick recap of what we saw in the last week, we we saw that we began. So basically, we began with something which is known as radiation fluxes, and we argued that when we are dealing in radiation heat transfer, uh, there are two things that comes into the picture and are often used when we are dealing with radiation. First, uh, whatever the fluxes we will consider, they mostly so depend. I mean, instead of some special cases, they mostly show dependence on the wavelength and on the direction. Okay, that is in the direction in which property is being looked at. The dependency on wavelength is known as spectral properties, as we have seen, and the dependency in direction, we have argued that basically they are dependent on the spherical coordinates in general, which are the zenith angle and the azimuthal angle, and the total dependency of this direction is attributed to something which is known as the total hemispherical, let's say, the total hemispherical property, which means that if we are now summing up all the contributions from each and every direction into a fictitious hemisphere that encompasses, let's say, a surface, then the total property that we would get from all the direction combined is known as the hemispherical property. And similarly, at the end of the class, I also said that we can also integrate the property along the entire band of wavelength, and then we will see that whatever the property that we will get, it's basically known as the total hemispherical uh, property that we are trying to see. For instance, if we are trying to calculate, let's say, the total, that means if you are, let's say, trying to calculate the emissivity along all possible, wavelengths and in the all possible directions, that is basically we are integrating along all these coordinates and along all the bands of wavelength, then the total emissivity is also known as the total hemispherical emissivity, to be precise. So this is something that we saw. So in a nutshell, it can be, so we can argue that the properties are in general a function of wavelengths and directions, and this is something that we didn't see when we learned conduction heat transfer. Keeping that in mind, we looked into the radiation fluxes, and we saw four important fluxes that we could categorize the entire radiation heat transfer into. The first was, if you remember, the first was known as irradiation, which is nothing but the energy that is basically falling on a surface. This is just termed as irradiation, and we argued that this energy can this energy can go in, so it can basically transmit across the medium. It can be absorbed by the medium, and some part of it can be reflected from the medium. So just by doing energy balance on a control surface, let's say, we said that this irradiation was equal to the transmitted irradiation plus the absorbed irradiation plus the reflected irradiation, and then dividing the total irradiation throughout this entire equation, we say that the transmittivity plus the absorptivity plus the reflectivity is equal to 1. And if my surface is opaque, which we will do so in most of the problems in radiation heat transfer, we said that the transmittivity will just go to 0, which means that the summation of your reflectivity plus absorptivity is always equal to 1. Then we looked into something which is known as the emissive power. And this is, of course, defined as the rate at which radiation is emitted from a surface owing to its own temperature per unit area. And we saw that by using the famous, Stephen Boltzmann relation, the emissive power of any surface is related to the fourth power of its absolute temperature, where Ts is its surface temperature, and it's the absolute temperature that we are looking into the picture here. And this constant, if we remove the proportionality, the constant is known as the Stephen Boltzmann constant, bearing the magnitude of 5.67 into 10 to the power minus 8, with its unit watt per Kelvin to the power 4 meter square. And if you are considering a real surface instead of a black body, then this emissivity also comes into the picture. And in fact, this emissivity is nothing but a total hemispherical emissivity that we will shortly see today when we will basically be dealing with properties of real surfaces. But nonetheless, this is basically so this equation basically tells you what will be the emissive power of any body that 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 possesses a an absolute temperature Ts. Okay, and thereafter, having been seen what irradiation and emissivity means, we saw something which is known as radiosity, which is nothing but the the radiation that leaves that leaves a unit surface area, uh, and it so you can basically argue that if I have now a control surface, what is the net, or it's not the net. The net is basically the difference between the irradiation minus radiosity. But if you just ask me, what is just the radiation that leaves that control surface? Okay, then this term is known as the radiosity, and as we have seen, this is also a flux quantity, meaning we are calculating it per unit area. And you can just establish this radiosity in terms of the emissive power and the irradiation that is falling on a surface. Okay, and this is its simplified form as we have seen. And nonetheless, as just what I said some few seconds back, we can also calculate the net radiative flux now, having known what is the irradiation and radiosity. And the net radiative flux is nothing but the difference between the radiosity and the irradiation. I'm sorry, I told the other way around some seconds back, but it's actually the difference between the radiosity, which is the radiant energy that leaves the surface, that leaves a control surface, minus the irradiation that falls on a control surface. Okay, and if you just simplify the expression of radiosity uh, into this and basically use the fact that you have an opaque surface and use the fact that the summation of all the fractions is equal to 1, you simply get an expression for the net radiative flux that leaves the control surface uh, in terms of these quantities like the emissivity. Of course, this is a constant, which is a Stephen-Boltzmann constant, and alpha, as you know, is the absorptivity. Now, I quickly said that there is a law which is known as the Kirchhoff's law, and if you use the Kirchhoff's law, of course the Kirchhoff's law is based on certain restrictions, but if you follow these restrictions, you can, as we will see today, you can basically also show that this alpha, which is the absorptivity, is equals to the emissivity sometimes. Okay, and this comes from the Kirchhoff's law, and we will see under what conditions today that this Kirchhoff's law is valid. And I believe you have also seen this in the lecture classes. So today's discussion on Kirchhoff's law, it can be a recap of something that we have already seen in this week's lecture series. But anyways, it will help you to solve the assignment problems as we have been doing it in the previous sessions as well. Okay. So with this, we move on to solving a problem involving these radiation fluxes. We'll not go into the nuances of this problem because we have already seen it in the last class. And then we looked into something that is very important, and uh, that is basically known as the radiation intensity and emission. Okay, so we define something which is known as the spectral intensity of emitted radiation. We call it I lambda E. And if you remember the definition, it was a little bit involved definition, I understand, but it is the most fundamental definition that you could have in radiation heat transfer. Okay, because it says that it's nothing but the rate at which the radiant energy is emitted at a wavelength lambda in a fixed direction, let's say theta phi, per unit area of the emitting surface, which is normal to its direction. This is an important term, and that's why we have this cos theta thing that comes into the definition of the spectral intensity of radiation. And it is per unit solid angle about this direction, and in the wavelength d lambda about this wavelength lambda. Okay, so this was the formal definition of the spectral intensity of emitted radiation, and we argued that if we now want to calculate the hemispherical, from the spectral intensity, we define something which is known as the emissive power, because you can always relate the emissive power to the intensity of radiation. And we argued that if we now want to establish what will be the emissive power in terms of the spectral intensity of radiation in onto a fictitious hemisphere, because we consider it as a hemisphere because we need to we need to bring in all the possible direction into which this radiant energy can basically move out. Okay, so if we think about all the possible directions, then the only shape that comes into our mind is a hemisphere. Okay, and that's why this is commonly known as commonly known in the literature as the hemispherical emissive power. Okay, and then we calculated in fact, we established how the hemispherical emissive power is related to the spectral intensity of radiation. And we argued that if we now have the case of a diffuse emitter, which means that my properties are independent of direction, you can eventually show that your emissive power is related to pi times the intensity of radiation. And either you can establish the spectral emissive power, or if you integrate it along all the wavelength, you can say that your total emissive power is equal to pi times the intensity of radiation. Okay. But remember, this is true only for a diffuse emitter, as we have extensively discussed it in the last class. We ended the discussion by solving a problem. Also, we looked into some properties of black body, but we solved the problem involving this. So basically, we just solved a problem in which there was a surface. It was diffuse. So it was a diffuse surface which was emitting radiation. We just saw that what. So we were asked to basically calculate what is the what. So how much. So first, we were asked to calculate what is the emission that is being coming out from this object is intercepted by the area A2, and the given area on this differential area is basically A1. Okay, meaning that A1 is also very small, uh, and that's why they are commonly known as differential areas. Okay, but our task is to basically evaluate what is the radiant. I mean, what is the radiant energy that is being intercepted by this A2 that is coming from A1, given all the directions and all these things is known. And we use the basic definition of the relation between intensity of radiation and the emissive power, of course, to formally calculate what would be the radiant energy that is leaving one will basically fall on surface 2 is something that we calculated. Okay, arguing, of course, using the argument that we now have a diffuse emitter, which is given in the question. And then we are asked to calculate the irradiation, which is nothing but this radiant energy divided by the area of object 2, which is nothing but the irradiation that is falling on the surface 2. Okay, so this is something that we did in the last week. We just had a quick recap. I'll stop here for some time, and then we'll begin with the contents for this week. If you have any doubts, feel free to ask it now, and or else we will proceed with something which is known as emission from real surfaces this time. And like there was a doubt in the last class what basically meant by the Kirchhoff's law and all those things, so we'll try to you know all will not formally derive the Kirchhoff's law because this is something that you already did, but we'll try to understand what Kirchhoff's law really was. And this would be also a good recap, doing the assignments that you are supposed to solve in this week. And yeah, so that's the agenda for this time, for this session. And but before that, if you have any doubts associated with either the last discussion or the assignments that you solve or the assignments that you're supposed to solve, you can feel free to ask here, or feel free to interrupt me at any point of time during the session, and I'll be happy to address your doubt. So we'll stop here for some time, and then we'll move into something which is known as emission from real surfaces, and we'll see what we'll do today. Meanwhile, I'll just check if the recording is going on or not. Okay, I think it's going on. All right. So if no questions, let's proceed with today's discussion. So what we will do is today we'll study emissions from real surfaces, which means we no longer have the luxury of assuming the surface to be a black body. But before that, we will look into an important concept that we missed in the last class, which is known as the band emission. And after we learn band emission, we will formally define what emissivity is. And you guys already know. We'll just have a quick glance on what emissivity means, solve some problem related to emissivity from real surfaces. Emission from real surfaces using the property emissivity of those surfaces, and see how basically you can define spectral properties out of it. And how can you basically define what is something known as spectral emissivity, or total hemispherical emissivity and things like that, just how we define it in the last class for a black body. And then move on to something which is known as the Kirchhoff's law and the gray surfaces, uh, which we will see shortly what basically this what is the implication of using the Kirchhoff's law and the fact that we may have a gray surface into the the radiant energy that is emitted from a surface. We'll look into that, and so if there is time, we will end this by solving a problem on irradiation on real surfaces uh, at at so this is the last thing that we'll do today, and it's in our plans. Let's see how far we can go, or else we will finish it in the next class. All right. So without any delay, this is the agenda that we are going to follow. I mean, this is the roadmap that we'll follow. So without any delay, let's get started to something which is known as band emission. Okay. So you need to understand that here is a plot between the spectral emissive power, okay, of a black body. So try to understand the band concept of band emissions can be extrapolated to any bodies. But here, in order to formally define the band emission function that we will see shortly, we will use the concept of a black body, and later on we'll see that it can be extended to any body just by using the term emissivity. Okay. So in this plot, there is a plot between the spectral emissive power of a black body denoted by E lambda B. Of course, it's a function of temperature, and that's why we are writing T here. And in the x-axis, we have just plotted the wavelength lambda. Okay. So there is a natural question that comes into our mind, that since this emissive power of this black body, okay, so first of all, it is not constant, okay, with respect to the wavelength. There is a curve that it follows. For instance, like there is a maximum of this emissive power at a wavelength lambda 1, okay, there is some value at a wavelength lambda 2, and slowly it decays to 0 if you kind of if you think that this curve basically comes down. It may or it may not comes down, but we are just telling it as an example. Okay. So the bottom line is that this spectral emissive power of this black body is showing variations with wavelength, which now means that I cannot, consider this as a gray body, typically because if I choose a particular wavelength, my spectral emissive power of this, my emissive power of this black body is different. So the natural question now arises that if I now want to ask you, okay, what is the energy, or what is the emissive power, in this range of wavelength from, let's say, 0 to lambda 1. So the question is, so what I seek is, so I seek the radiation emission in the spectral band which is from 0 to, let's say, lambda 1, okay, which is basically this band. Okay, that means I'm simply asking you that what is the emissive power in this band of in this band of wavelength from 0 to lambda 1. So can you tell me how can we evaluate this emissive power based on this figure? It's evident, right? So what would be this emissive power? Can you tell me geometrically at least? So what do you think? So at least geometrically, what do you think this is? So if I want to find out the radiation emission in the spectral band of 0 to lambda 1, which is basically this, what do you think is the geometrical interpretation from this graph? Any idea? So what we are okay. Yes, exactly. So integration from, okay, yeah. So that's the mathematical. You are true, Sanvi. It's the mathematical implication of. So basically, what Sanvi is saying is that we just need to integrate. Okay, we just need to integrate 0 to lambda 1 is EB lambda, because it's a function of lambda, as we have seen, and we'll integrate it by choosing an infinitesimally small wavelength d lambda. So the idea is that we'll just choose a small strip of wavelength, calculate this EB lambda here, and then we'll basically integrate this from this band, which is basically from 0 to lambda 1. So geometrically, it is just the area under this curve. That's the thing that we're evaluating, right? So EB lambda, so when you are just choosing this d lambda, and this EB lambda times d lambda is the area of this differential strip, and if you are just integrating it, it simply comes out to be the area of the curve. Okay, so which means which now means, okay, that if I now, so can you tell me, if I now if I now ask you what will be the total radiation emission from the entire wavelength? So is it a way of saying that if I just integrate this, if I just integrate this, okay, so this is the answer to, okay, so this is the answer to uh, radiation, radiation emission from 0 to lambda 1. Or you can interpret as radiation emission is nothing but the emissive power. So you can say that it's the emissive power from 0 to lambda 1, which is basically in between the wavelength 0 to lambda 1. So now can you tell me, if I now in the same script, if I now ask you what would be this term, known as? So the question is, if I, instead of integrating it from 0 to lambda 1, if I integrate it up to 0 to infinity, what do I basically get? So you can appreciate that this is nothing but the total emissive power. Okay. And can you tell me what this total emissive power simply, simplifies to in case of a black body? Or I'm asking you what this integration leads to. Integral 0 to infinity EB lambda d lambda. This we have seen in the last class, if you remember. Yes. You just need to little bit think that for a black body, if I integrate, so it's just the same thing. I choose a differential strip, okay, and then integrate this differential strip throughout the entire range of wavelength from 0 to infinity. Okay. In that context, can you tell me what this leads to? So the question is, what is it? Yes, exactly. It just leads to the Stephen Boltzmann law, okay? So it basically leads to sigma times temperature of the black body raised to the power 4. Okay, it's obvious, right? Because we know that the total emissive power of a black body is nothing but the sigma times its 4th power of its temperature, which means if I now pick a spectral band, okay, of the spectral emissive power and integrate it along the entire duration of the the entire band of the wavelength, it just gives me the total emissive power of a black body, which now means that I can now define a fraction, let's say f 0 to lambda 1, which just gives me the the fraction of energy, and by energy I mean the fraction of emissive power, which is in between the band 0 to lambda 1, okay, eb lambda, which is a function of lambda, of course, d lambda, divided by the total energy, or to be precise, the total emissive power, which is nothing but my integral from 0 to infinity, okay, eb lambda, which is of course a function of lambda into d lambda, which now means that if I just use the Stephen Boltzmann law, as you have correctly pointed out, this f 0 to lambda 1 is nothing but the integration from 0 to 0 to lambda 1, okay, eb lambda, which is a function of lambda d lambda, divided by sigma times eb raised to the power 4. And this is the precise definition of something which is known as band emission, where this f 0 to lambda, okay, this f 0 to lambda just tells me the fraction of emissive power, okay, that is in the band, okay, 0 to lambda 1, okay. Or in other words, if you look into the graphical aspect, the graphical picture, it tells you what is the so it tells you the fraction of area that is being intercepted by this wavelength up to lambda 1 with respect to the entire area that basically did curve, this curve, and with respect to the entire area that falls under this curve. Okay, so needless to say, since this area is obviously less than the total area, this band emission function is a fraction basically. Okay, and of course it also, like in using a simple energy balance also, you can simply justify that, since I'm just now interested in finding out what is the emissive power in between a wavelength from 0 to lambda 1, it will obviously be less than the total emissive power, where you need to now integrate from 0 to infinity, which is basically nothing but the sigma times TB raised to the power 4. Okay, so this is the formal definition of something which is known as band emission function. Okay, now the question is, although we have formally defined this band emission function, now how do we basically calculate this fraction? Okay, or how do we basically calculate that what is the fraction of the emissive power that is lying from 0 to lambda 1? Okay, for that, in order to calculate this, in order to calculate this integral, to be precise, you need to know this value, and of course this value is known because the temperature is generally known in these cases. Okay, and for that, there is a table which you basically need to learn how to see that table, and I hope you have learned that already in the theory classes, but we will just have a quick recap of this. So what people do is they multiply this equation by a TB and TB uh, into the numerator and denominator. So what we are doing is we are multiplying this equation by TB in the numerator and in the denominator, which means this f, 0 to lambda 1 reduces to integral, you know, EB lambda. And since my temperature is independent of the wavelength, so this multiplication, so this TB can be brought inside this, differential wavelength that I'm considering. So it can now be written as EB lambda d of lambda TB, divided by sigma times TB raised to the power 5. And since now, this differential wavelength which we are considering has a prefactor this multiplied, which is TB. So this integration will also now take place from 0 to some lambda times TB. Okay, and this is done because you can show that this f0 to lambda 1 is now some function which is basically a function of lambda and TB. Okay, this is just a way of mathematical way of showing that this band emission function can be determined once you know what is the wavelength and what is its corresponding temperature. Okay, so once that is known, you can basically calculate. So there is a table. I will quickly show you the table. uh, you have also seen this table in the lecture classes, but anyways, we'll see what this table looks like. But the bottom line is that if you know the corresponding wavelength and you know the corresponding temperature, you know there is a functional relationship between this band emission function and these values. Okay, and this is sufficient to give us what is the fraction of energy that lies between a wavelength 0 to lambda 1 with respect to the entire total emissive power, which is nothing but the sigma times T raised to the power 4. Okay, so since I was talking about the table, so this is a particular table that you need to look at. Okay, so let's say let's say I know this corresponding wavelength and the temperature of this corresponding wavelength, which means I indirectly know this value of lambda and TB. So if you know this value of lambda and TB, let's say I know the wavelength and I know the temperature, which means let's say I know these values. Okay, so once you know these values, you can correspondingly calculate what is the corresponding value of this fraction from these kind of tables. Okay, and this table is taken from the book of Impropera, and you can see this, and I think it's also there in the website of the course. It's readily available. It's there in the lecture notes of the theory classes as well. So the thing is, once you know this value of lambda times T, you can corresponding calculate what is the fraction that is falling in between the wavelength from in between the prescribed wavelength that we are kind of looking at. Okay, and this is the idea behind this band emission function and how to evaluate this fraction from these kind of tables, solely because you now have, although this exact functional form is not known. Okay, so they have not stated this exact functional form, meaning that how basically this function, so how basically these values are related to these values, so they are not exactly known. The exact functional form is not known, but you can still use these tables to calculate your fraction of wavelength lying between, a particular band, to calculate the fraction of emissive power lying between a particular wavelength, once you know the multiplication of lambda and the temperature, okay, from these tables. Just because there is a functional relation that occurs between this lambda times dB and f0 to lambda. I hope this is clear to you. So if this is clear to you, and if there are no questions, can you tell me how to calculate this fraction? If I now ask you to calculate this from, instead of 0 to lambda, if I now ask you that they are falling in between two wavelengths, lambda 1 and lambda 2, or in other words, if I ask you that what is now the fraction that is between, that is lying between these band of wavelength, or what is the area of this curve that is falling here? So now can you tell me how can you do that? The interesting thing is that it is not now from 0 to lambda 1, it is between this lambda 1 and lambda 2. How can we get that? So can you tell me how? So I'll just simplify this. You can simply write this f, lambda 1 to lambda 2 as, just by following, the principle of integration, as 0 to lambda 2, okay, eb lambda d lambda minus integral 0 to lambda 1 eb lambda d lambda divided by the total thing, that is 0 to infinity eb lambda d lambda, which just simplifies to, something which is known as the sigma times t raised to the power 4. So this integral basically simplifies to f lambda 1 to lambda 2, which is nothing but integral 0 to lambda 1 f eb lambda d lambda divided by sigma t raised to the power 4 tv raised to the power 4 minus integral 0 to lambda 2 eb lambda, sorry, this should be lambda 2 because 2 is higher than lambda 1, lambda 2, and this should be lambda 1, lambda 1 eb lambda d lambda divided by sigma times dv raised to the power 4. Okay, so now can you tell me what is this? So you need to tell me what is this in terms of this fraction f, and what is this in terms of this fraction f. We just now saw that, right? So what is this in terms of this fraction? Yes. So we just now saw this, right? So this basically is equal to this, and this is of course lambda 1. So can you tell me, we just saw that integral 0 to, or let's say we see here, okay, we saw that integral 0 to lambda 1 eb lambda d lambda by this thing is f0 to lambda 1. Okay, so what is this basically? So if this integral, if this integral, so it tells that if I integrate from 0 to lambda 1, okay, the spectral emissive power, okay, divided by the total, emissive power, I get the fraction of energy that is between 0 and the corresponding wavelength lambda 1, which means I can simply write down this f lambda 1 to lambda 2 as, this integral can simply now be written as f 0 to lambda 2 minus f 0 to lambda 1. It just speaks, so what does this speak? It just speaks that what is the band, okay, or what is the fraction of energy that lies between the integral, lies between the band 0 to lambda 2, and if we subtract that, that is lying between the band 0 to lambda 1, that we already, calculated before, we can simply get what is the, fraction of energy that is lying between the wavelengths lambda 1 and lambda 2. So this is a very, important results associated with the band emission function, that if you, because see, the table does not speak, the emission function between two corresponding wavelength. It just speaks that if my wavelength ranges from 0 to a certain value of my wavelength, what is my corresponding fraction? Okay, that is, so you can appreciate this from this table. That is a table that we, just now saw. So so this fraction is always from, a value 0 to lambda. Okay, it is not from a value lambda 1 to, let's say, lambda 2. So when you need to calculate it from, in between two wavelengths, you need to, subtract the fraction of the greater wavelength to the fraction of the, lower wavelength, and then you will, basically get what is the fraction that is lying between two particular wavelength. Okay, and this is an important property, and it is just the principle of integration that we have used, you know, to come up with this particular relation. Okay, and we will shortly see through a numerical how these kind of relations are applied. Okay, but yeah, this is something that you need to understand. Okay, so I repeat, if you want to calculate the fraction of energy that is lying between two corresponding wavelength, you need to subtract the fraction of energy that is lying between the higher wavelength minus the fraction of energy that is lying between the lower wavelength in order to get the fraction in between the spaces of the two wavelengths that we are kind of considering. For instance, this is shown by this graphical implication that if I now want to calculate these blue area, I just need to basically know what is my f 0 to lambda 2, and then I will just subtract my f 0 to lambda 1. Okay, and if you know this lambda 2 and lambda 1, which obviously you do, and of course you know the temperature, you can find out this fraction very easily because you just need to see what is the product of lambda b and t, and if you know this, you basically know f from the table. Okay, and then you can basically calculate this fraction corresponding to these two given value of wavelength, and then you will know what is this fraction of energy that is lying in this space in the graph. Okay, I hope this is clear on the band emission function. I'll stop here for some time. If you have any doubts, you can ask me. And then we will now formally define something which is known as emissivity, and and then we will see a numerical associated with this thing. Okay. Okay. If no doubts, then we now define something which is known as emissivity, because all these analysis, that is all these things that you wrote, that is the things that we did here, these are true for a black body. So if you want to do the same kind of things for for real surfaces, we need to define properties associated with real surfaces. Okay, and one such property that is most commonly studied in radiation heat transfer is known as emissivity. Okay, and this is generally denoted as epsilon. And just like the intensity of radiation or the emissive power, emissivity can also be defined as the spectral emissivity and the total hemispherical emissivity. Okay, so formally what I will do is, and as you guys have as you have seen in the lecture classes, this emissivity in general, if it is defined in this form, that epsilon is nothing but the ratio of et by ebt, then this emissivity is known as the this is known as the total so this is basically so it's just called the total hemispherical emissivity. Okay, which just says that, so it is defined as the total hemispherical emissivity, typically, again, because you are taking into the corresponding contributions from all the directions, and that's why it becomes the hemispherical emissivity. And it just says that the emissive power, that is what is, so it is just the ratio of the total hemispherical emissive power of a real body to the total hemispherical emissive power of a black body. Okay, and this is what and this is what the total hemispherical emissivity signifies, which is, again, I repeat, it is the emissive power, the total emissive power of a real body to the total emissive power of a black body. Okay, total means the total hemispherical emissive power. Okay, so so as I said, this is nothing but your total you know emissive power, and this is your emissive power, of course, of a real body, and this is your total emissive power of a black body. And remember, remember meaning, try to appreciate that when I say it's the total emissive power, it means it is independent of direction and it is independent of wavelength. Independent means we have taken into the contributions, it's not independent, to be correct. It just means that we have taken the contribution from the entire band of wavelength, okay, and the entire, and the entire possible direction. Okay, that's the basic idea. And if we just calculate the ratio of these two emissive power, it just gives me the total hemispherical emissivity of a real surface. Okay. Again, can you tell me what is this that you just now said? What is this? The total emissive power of a black body. That is again this sigma times TB raised to the power 4, right? That I mean you only just stated sometimes back. Okay. So yes, exactly. So this means I can simply write down that my total hemispherical emissivity is equal to, you know, this ET, which is the, total emissive power of a real surface divided by this, no, divided by this sigma times T raised to the power 4, TB raised to the power 4 to be precise, which gives me, the total emissive power, total hemispherical emissive power of a black body. And the word hemispherical doesn't come into the picture of a black body typically because a black body is a diffuse, so it's a diffuse emitter. So you can just say it's a total emissive power of a black body. And then, so this is one form of the definition of the total hemispherical emissivity. And then what you can do is you can write this ET, okay? You can simply write this ET into something like this: integral 0 to lambda, okay? E lambda, which will now becomes a function of lambda and t times d lambda, okay, divided by sigma TB raised to the power 4, which means you can write the total emissive power of a real surface as the integration. I mean, this should not be lambda actually. I mean, in principle, this should be up to infinity, because what you are doing is you are just writing the total emissive power, okay, the total emissive power of a real surface in terms of the spectral emissive power when integrated, along the entire band of wavelength. Okay, so it just says, that you can relate the total emissivity, okay, into the spectral, the spectral emissivity of a real surface in terms of like when you integrate this along the entire band of wavelength. Okay, so this is one, so it's kind of one more form of this particular equation that you guys saw. Okay, the basic equation is just the same. The basic equation is just this. We are just writing one terms in terms of the another. Okay, and as I said that you can always write your total property in terms of the spectral property, and the integration of the spectral property along the entire band of wavelength gives you the total, the total property. And this is something that we have done. Okay, so in that context, you can also now define something which is known as the spectral, the spectral emissivity of the real surface as E lambda, which is nothing but your, this thing, this spectral emissive power, which is of course a function of lambda and T, divided by the spectral emissive power of a black body, which is nothing but EB lambda, which is of course also a function of now lambda and T. Okay, and these definition of the of these two ratios, which is nothing but the spectral emissive power, okay, of a real body to the spectral emissive power of a black body, is known as the spectral emissivity. So it's just that one definition comes from the other. That's what we are just seeing. Okay, so this is known as your spectral emissivity. Okay, all right. So this is one definition of your emissivity. So see, do not blindly kind of memorize all these definitions. Start from the basic definition of total emissivity of a real surface, and then come to the spectral properties. Okay. For instance, like if I integrate my spectral property with respect to the entire band of wavelength, I get ET, which means now I can formally define what is this E lambda T as a ratio of the spectral emissivity of the real surface to the spectral emissivity of the black body. Okay, and then this is known as your spectral emissivity. Okay, so we saw two things. First, the total hemispherical emissivity, and this is its basic definition, and also the spectral emissivity. Okay, now you can also define something which is known as the spectral directional emissivity. Okay, and it is now defined as epsilon lambda theta, because it also now shows directional dependence. And of course, since it is now a function of your lambda, theta, phi, and of course your temperature Tb. Okay, and this is nothing but it is the same analogy that we have drawn. If you just do a one-step simplification, that you can write your spectral power as your, as your directional properties. If you integrate it over the entire direction, you just get your spectral power. And then you can define what basically is your directional property in terms of this spectral directional emissivity. It's the same drill that we need to do again and again. So it's like we are starting from you are starting from the total properties, and then slowly doing a step down to the specific properties. For instance, we started off with total total hemispherical emissivity, came down to what is known as the spectral emissivity, and one step below we come into something which is known as the spectral directional emissivity. Okay, so the spectral directional emissivity can now be easily defined as the ratio between I lambda e, because when you comes into the direction, you need to come into something which is known as the intensity of radiation, and not just the emissive power, because now it show directional variations as we saw it in the last in our last discussion. Okay, so it becomes I lambda e, which is of course a function of lambda, theta, phi, and Tb, to the ratio of I lambda b, which denotes the so it basically denotes the radiation intensity, or the intensity of radiation of a black body. And can you tell me, is this correct or is this wrong? Or I can just write this as write just this as this. Okay, is this correct for a black body? The simple question is that can I just write the intensity of radiation of a black body, uh, or can I say that the intensity of radiation of a black body is not a function of theta and phi, or simply I just remove this theta and phi? Yes. Why is this so? Why is my intensity of radiation of a black body independent of direction? Because I mean, I mean, few seconds back, yes, exactly, it's a diffuse body. That is exactly correct. Okay, and we have seen that a black body emits diffuse. A black body is a diffuse emitter, and that's why it emits radiation in all possible direction, and that's why the intensity of radiation of a black body is not a function of direction. Direction meaning the zenith angle and the azimuthal angle. Okay, so very nice. So these are the conceptual things that you also need to appreciate. So this means that I can write down the spectral directional emissivity as this lambda theta phi Tb as the intensity of radiation for a real body, which is of course a function of lambda theta phi and Tb, to the intensity of radiation of a black body, and this is of course a function of lambda and Tb. So this is the formal definition of something which is known as the spectral directional emissivity of a real surface. Okay. All right. So this, as I said, is known as your spectral directional. Yeah, that is true. Essentially, that is true. Thank you for the correction. There should not be TB in numerator because it's just the temperature. Okay, this is correct, right? Now is this correct? And actually, you need to compare the same temperature. So it is more correct if I just write it, if I just leave it as it is. So can you say is it fine now? Is this fine now? Yes. Okay. Thank you very much. Yeah. Thanks for the correction. So this is your spectral directional, you know, emissivity. All right. So what we did is we started off with the total hemispherical emissivity and saw, and went into a couple of steps, steps down and saw what is the spectral, directional emissivity uh, of real surfaces. Okay. So we saw three things. First, the basic definition, which is the total hemispherical emissivity. And as I said, it is nothing but the total emissive power of a real body to the total emissive power of a black body. And when I say total, you are, considering the culminating effect of all the possible direction and in all the possible wavelength. Then we went a step down that, okay, now let's see if I can define something which is known as the spectral emissivity, which means that I can now define the ratio of the spectral emissive power of a real body to the spectral emissive power of a black body. Okay. And then we move one step more, we just went one step more and see that, okay, now can we also bring in the directional effect of, the emissivity into the picture. And for that, we define something which is known as the spectral directional emissivity in terms of the intensity of radiation of a real body, which is of course now dependent on the directions and also the corresponding wavelength, to the intensity of radiation of a black body. And as we know, the black body is a diffuse body, which means that my intensity of radiation is, you know not a function of the direction, meaning the zenith and the azimuthal angle. And then we formally saw the definition of the spectral directional emissivity to be just the ratio of the intensity of radiation of a real body to the intensity of radiation of a black body. Okay. All right. I hope this is clear. So if this is clear, okay, we will now solve a prototypical example of these things that we just saw. Okay. And these kind of examples are there in your assignment. I mean, this exact problem is not there, but a problem analogous to this problem is there in your assignment. And if we solve this, it will be helpful for you, I believe, to solve the problem in the assignment, in your assignment, basically. Okay. But before this, I'll stop here for some time. If you have any doubts, you can ask me. Uh, I'll also come in just 2 minutes. I'll just fill my mug and come in 2 minutes. Okay. All right, guys. Sorry for the interruption. Let's see if there are any questions. Okay. Okay. If there are no questions, let's go ahead and solve a numerical. So as you can see in your screen, so there is a question which says that a diffuse surface at a given temperature, which means the temperature is known to us, which is 1600 Kelvin, has a spectral and hemispherical emissivity shown as follows, which means that the emissivity is just the spectral hemispherical emissivity, meaning that it has just defined that E lambda that we just now saw. Basically, it has just defined this quantity. Okay. So it says that the spectral hemispherical emissivity is something like this. Okay. Now, if this is the case, what they're asking us is that determine the total hemispherical emissivity and the total emissive power of this diffuse surface. It has said that your surface is a diffuse surface, uh, and that they have a priori mentioned in the question. Okay. So the task is, as I said, the task is to basically calculate uh, the total hemispherical emissivity, meaning you need to calculate, you know, so to find, you need to calculate your epsilon, the total hemispherical emissivity, and the total emissive power, which is E as a function of temperature, of course, which is ET basically. Okay, these are the two things that you need to find. Okay, and of course, that is something that you need to do. Given that, so it has said that the variations in your spectral hemispherical emissivity as a function of wavelength is like this. So from wavelength 0 to lambda 2, sorry, for wavelength 0 to lambda 1, which is 2 micrometer, your emissivity, your spectral emissivity is some constant epsilon 1. It is some other constant epsilon 2, and it is the next, and of course, it is 0 here when the wavelength ranges from 5 to basically infinity. Okay, so this is what they're asking you to solve for. And although they have so you can appreciate that your epsilon 1 is 0.4 and epsilon 2 is 0.8. That is from the figure. So I'll just write it down for the sake of clarity. Your epsilon 1 is 0.4, your epsilon 2 is 0.8. So I hope the question is clear. I repeat once again, the given plot is a plot between your spectral hemispherical emissivity of a real surface, of course, as a function of wavelength. I call it a real surface because it have a emissivity which is not equal to 1. They're simply asking you that given that it's a diffuse surface at a prescribed temperature 1600 Kelvin, okay, and you know the bands of wavelength, they're asking us to calculate the total hemispherical emissivity and the total emissive power. So for our emissive power, we need to calculate the total hemispherical emissivity first, and then we need to use the Stefan-Boltzmann law to basically calculate what the total emissive power will be. Okay, so any idea how do we solve this? So what do we need to use that we discussed today in order to solve this problem? That's the first thing, that I'll ask you. Of course, before that, remember that they have said that it's a diffuse surface, meaning that there is no directionality dependencies that will come into our problem. Okay. All right. Okay. So what do we need to do? How do we calculate it? Any idea or any suggestions? I hope you have gone through the problem at least, and at least you are clear what do we need to do. Yes. So let's proceed it systematically. Okay, so it is exactly, we need to proceed it exactly in the ways that we have just defined the emissivity, some minutes before. So we will start off with the form. So what do we need to calculate? We need to calculate the total hemispherical emissivity. So we'll start off with the definition of the total hemispherical emissivity itself. So we know that the total hemispherical emissivity epsilon that we just now saw, right? I mean, some pages before, that is basically this. Where is it? It is it's this. Okay, it's this, or you can just write it in terms of this in whatever manner you want to write. Okay, so so my total hemispherical emissivity can be written as the emissivity, the total hemispherical emissive power of my real body to the emissive power of a black body at the corresponding temperature. Okay, and then I can write this ET as an integral from 0 to infinity. Okay, what I can write? I can write it as this EB lambda, okay, times, so I can write it as, this it will not be B, it is just the integration of the spectral emissivity of the real surface, E lambda, which is of course now a function of lambda times d lambda divided by this EB as a function of t. It is nothing. So please be very clear that this ratio is the ratio of the total hemispherical emissivity of the real surface to the total hemispherical emissivity of the of the black surface, to be precise. And then I am writing this ET, that is the total hemispherical emissivity of the real surface, in terms of the spectral emissivity of the real surface. Okay, that if I integrate my spectral emissivity along the entire band of wavelength, it just can be written as something like this. Okay, that I mean you are just clear with whatever we are doing so far. Okay, and then what I will do is this can now be written as something like this. It can now be written as integral 0 to lambda the spectral emissivity times the so if I bring in the spectral emissivity into the picture, I can now write it as E B lambda d lambda, sorry, E B lambda d lambda divided by EB, which is of course just a function of temperature. Okay, so is it clear up to this point how we reach this stage from this stage? Can you just tell me with an yes or a no, or do I need to repeat it again? I mean, are you clear? So we define uh, this spectral emissivity of the real surface in terms of this total emissivity of the real surface, because we know that if we integrate the spectral emissive power of a real surface along the entire band of wavelength, we get the the total emissive power of a real surface. Okay, now from this I can use the definition of spectral emissivity that we just now saw, because we know that, because what do we know? We know that this spectral emissivity, okay, is nothing but the ratio of the spectral emissive power of of the body. This is of course a function of lambda and t to the spectral emissive power of a black body, which is of course a function of lambda and t itself. From there we introduce this EB lambda, because I know that my E lambda, which is basically this, is just EB lambda multiplied by this spectral emissivity. So is it clear? Yes. Okay. Thank you very much. All right. So now what we will do is we'll do one thing. Okay. So this equation that we just now wrote here, we know that this E lambda, okay, which is nothing but the spectral emissivity, it in general is a function of lambda, that we know. But if we see this figure, okay, if we see this figure from the band 0 to 2, or let's do this. Okay, let's write it systematically. So I can just write it as integration from 0 to 0 to 2, because now I have this E lambda, which is basically given in the problem. See, this E lambda is given to a problem. Okay, I just want to know what is this epsilon. E meaning, sorry, I am saying E, it's not E, it is epsilon lambda. Okay, so so the question wants us that epsilon lambda as a function of wavelength. You just need to use this relation to basically calculate what is the total emissivity, okay, of the real surface. So what I am now doing is I am simplifying uh, this integration in terms of these step functions basically. Okay, so please let me know if you are clear to this point or not. So this integral 0 to infinity, okay, this epsilon lambda ev lambda d lambda can be now written as integration from 0 to lambda 1 epsilon corresponding to the to the wavelength lambda 1 times eb lambda d lambda plus integral from you know how can we write? So it is integral from lambda 1 to lambda 2 epsilon corresponding to the second band. We'll just write it as epsilon lambda 1 to 2 times eb lambda d lambda divided by, of course, there should be this divided by eb times t. We'll not bother about the wavelength from lambda greater than lambda 2 typically, because this is just 0. Okay, so we are just interested in this zone and in this zone. Okay, so please let me know if you are getting this step, or did you understand how do you get this step from this particular step. We are just dividing the integral in terms of the zones that we are given. Basically we are just writing it for this zone, which is basically this, plus this zone, and the rest we are not bothered because this is just equal to 0. So this total integration we have just divided into the first zone, and this is for the second zone, where I know this lambda 1, remember this lambda 1 is equal to what? It's equal to 0.4 micrometer, and this lambda 2 is equal to, sorry, I wrote it wrong. My lambda 1 is 2 micrometer, right? So this is my band of the first wavelength. So it is 2 micrometer, and is, I mean, okay, you can just write it as 2 micrometer, and then lambda 2 is basically from, 2 to 5 micrometer to be precise. Or I should write, okay, it's not good to write in this manner. I should write it as, so my first zone, so the first zone is, wavelength ranging from 0 to 2 micrometer, and my second zone is wavelength ranging from 2 to 5 micrometer. I think that is the correct way of, representing it. All right. Okay. So we'll simplify this and let's see what do we get. Okay. So this can now be written as, so I'll just divide these integrals. So this can now be written as, EBT. Okay. And we have this integral 0 to lambda 1, epsilon lambda 1 times of EB lambda d lambda, okay, plus this can be written as integral from lambda 1 to lambda 2, okay, epsilon from lambda 1 to 2 times of EB lambda d lambda, okay, divided by EB raised to the power 4. Okay. So we just did nothing. We just segregated these fraction and these fraction. That's it. That's all we did. Okay. Now please observe and tell me if I'm correct or not. For this integral, from 0 to lambda 1, can I write this as like this or not? Epsilon lambda 1 integral 0 to lambda 1 EB lambda d lambda divided by EBT. Is this correct or not? Or I did some mistake here? The simple thing is I brought this E lambda 1 outside this integral for the given range from 0 to lambda 1. Is it correct? Or I made a mistake here? And for this answer, you need to closely observe this figure. That what is happening between 0 to 2 micrometer, which is my lambda 1 to be precise. So this is your lambda 1 and this is your lambda 2. So see, when I move from 0 to lambda 1, my spectral emissivity in the range from 0 to lambda 1 is not a function of lambda, it's just a constant, right? So although in the total range it is showing a variation with respect to its wavelength, but in this zone from 0 to lambda 1, my spectral emissivity is just a constant, which means I can take this spectral emissivity only for the zone in between 0 to lambda 1 as outside this integral. Okay, is it clear or not? I mean, did you understand this point? You simply cannot take these as outside of this integral, typically because in the entire wavelength the spectral emissivity, it's a function of wavelength, but in between these zones it's given in the question that the spectral emissivity is just a constant. For instance, if I looked into the zone from 0 to lambda 1, the spectral emissivity it is just 0.4, okay, which means I can just take this outside of my integral and this just simply becomes this ratio. Is it clear? I hope it is clear. Uh, if you have any questions, just feel free, or if you want me to, tell it again, please feel free to let me know. I hope this is clear. And then in the same spirit, I can write down the second term as something like this. Please let me know if it is clear or not. I can write this down as epsilon for lambda 2, because in the second term as well, okay, this emissivity is not a function, the spectral emissivity to be precise is not a function of lambda, it is just a constant when you are in this band from lambda 1 to lambda 2. Okay, I hope you are clear with what I mean to say, or at least what the question is trying to say. So this becomes an integral from lambda 1 to lambda 2 EB lambda d lambda by EB t. Okay. So these, so the transition from this step to this step is very important. And you need to understand why we essentially did this. Okay. We did this, again I repeat, we did this typically because in the wavelength band from 0 to lambda 1, from the figure we saw that your emissivity, your spectral emissivity is just a constant. Okay. And that's why we could remove this E lambda 1 outside the integral, and the same business we did it from the second range, that is in the second zone. Okay. Because of the fact that when we move from, when we are in this zone, my emissivity is just this 0.4, and so is the case for the second zone where my emissivity or a spectral emissivity is just 0.8 to be precise. Okay. All right. Now can you tell me what is this? If it's clear, please let me know. If I need to explain it again, I'll be happy to do that, but I hope it is clear to you that why we basically did this. And if you are clear, can you tell me what is this? We just now saw, I mean, not just now, we saw it some 45 minutes back. What is, so what is this ratio? First of all, it is the ratio of the fraction of, you know, so it's the ratio of the fraction of the the emissive power that is lying in between the wavelength 0 to lambda 1 to the ratio of the, to the, you know, the emissive power of the entire spectrum, basically. What is this? So please have a closer look. I repeat again, it's the ratio, okay? It is just the ratio of the emissive power, okay, of a black body, which is in between the spectrum 0 to lambda 1 to the emissive power, you know, to the total or you can say it's the total emissive power of a black body, which is basically EB times T. Okay. So what is this? Can you recollect what we did, you know, so what we did at the first, you know, first part of the of this discussion? So we saw something which is known as band emission, if you remember. And is this nothing, is this just similar to the band emission that we saw? It is simple, of course, it is similar, right? Because it is just the ratio of the emissive power of a black body. Yes, exactly. Yes, it is indeed similar because it is just the ratio of the emissive power of a black body which is lying between the wavelength ranges ranging from 0 to lambda 1 to the total emissive power. Okay, so this is nothing but, you know, f 0 to lambda 1. It is the same band, you know, the band emission band emission function that we just now saw. Okay, and similarly, if you use the principle, you know, the integration principle that we saw, this is nothing but your f lambda 1 to lambda 2, which means I can write, this is a very important result, I can write my total hemispherical, you know, emissivity as my spectral emissivity ranging from the wavelength 0 to lambda 1 times the band emission function ranging from, you know, the same wavelength range plus the same business for the other part, the spectral emissivity in the wavelength lambda 2 times my f lambda 1 to lambda 2. Okay, and as I said, this is not directly known, and we have to use the same principle that we discussed, you know, some time back, that this can be written as epsilon into, you know, epsilon 1 times f 0 to lambda 1 plus this epsilon 2 into this f lambda 1 to lambda 2 can now be written as f, you know, 0 to lambda 2 minus f 0 to lambda 1. Okay, and this is the expression, okay, this is the expression for the hemispherical emissivity in terms of the spectral emissivities in the given ranges that the problem has asked us, or the problem has given to us, and the total, you know, hemispherical spectral emissivity that we need to find. All right, now the only thing that is remaining for us is to basically calculate this f0 to lambda 1 and this f0 to lambda 2. Okay, and that is very easy because, as I said, that we know from the figure that from 0 to this, that is from 0 to lambda 1, what do we know? We know the temperature, which is 1600, and we know the wavelength lambda 1, which is 2 micrometer, which means I can just say that from, you know, 0 to 2 micrometer, I know the product of my lambda times temperature. So what this would be? It would be just 2 micrometer multiplied by the corresponding temperature, which is 1600 Kelvin, which means it just turns out to be around 3200 micrometer. And from the table that you just saw, that once you know the product of this lambda times t, you can directly evaluate this, f0 to 2 micrometer from the table, because once you know these values, okay, if you see the table once again, once you know these values, okay, once you know these values, you can correspondingly calculate what is f0 to lambda basically from here. Okay, this table is not just finished here. There are certain terms. I'm just showing you a prototypical example of the table. Okay, you can have a look at this table in the book of Incropera, and once you know this lambda times t, you correspondingly know what is f0 to lambda. Okay, so for this case, when your lambda times t comes out to be 3200 micrometer from the table, your f0 to lambda comes out to be around 0.318. And in the same spirit, okay, in the same spirit, if you calculate, so this is your lambda 1 times t to be precise, and if you calculate your lambda 2 times t, which turns out to be around 8000 micrometer Kelvin, your f, so this should be 1, it should be 1, and this f0 to lambda 2, for this corresponding value of lambda 2 times t, your f0 to lambda 2 comes out to be around 0.856, which means now you know everything. You know all these values, f0 to lambda 2, f0 to lambda 1, and all these emissivities, because emissivities are known, right? For the first case, your emissivity epsilon 1 is 0.4 and epsilon 2 is 0.8, which means you just need to substitute the values here in this entire expression to basically get epsilon. So now your epsilon just becomes, you just substitute the values for the first term. It is epsilon, so it is e lambda 1, your e lambda 1 is 0.4, is 0.4 times f0 to lambda 1. F0 to lambda 1 is 0.318. So it's 0.318 plus your second emissivity, that is emissivity in the second, spectral band, which is nothing but 0.8, I think. Okay, so it is just 0.8 times. It's just the difference between this f0 to lambda 2 minus f0 to lambda 1. So your f0 to lambda 2 is, 0.856 minus your f0 to lambda 1 is 0.318. And if you just do this simple math, you will see that your total hemispherical emissivity simply comes out to be 0.558. Okay, this is the answer to the question. So it's a very beautiful question, which just says that once you know how your spectral emissivity varies, you can essentially calculate, okay, varying means the spectral emissivity varies with respect to the wavelength. You can essentially calculate what is the total hemispherical emissivity. Of course, you need to consider that your body is diffuse. That is one thing, and one approximation that I will discuss with you, that see, in general, in reality, this E lambda is not these straight lines, but for these straight lines are essentially crucial in our question, because we essentially took out the spectral emissivity in this band outside the integral, if you remember. So what people do is, in general, these variations are something like this. It is something like this. But people map this in terms of, so these are known as step functions. Okay, people map this in terms of the step function, typically because it makes their analysis easier. Easier in the sense that we could now take the spectral emissivity for this band outside this integration, if you remember, basically this step. And this step is the most crucial step of this problem. Okay, if you, let's say, have a emissivity of these kind of sorts, you cannot simply take it out of the integral, and then you cannot introduce the band emission function for black bodies, which we basically did here. Okay, which we did here. Okay, so this is very important. So what they do is, generally the emissivity variations are something like this. Okay, they are kind of like this. So if you look into the internet, the variation of spectral emissivities of any bodies, let's say with as a function of wavelengths, it's kind of like this. Okay, it's kind of like this. So they are not exactly step function, but you can map a step function from these variation as an approximation, so that your analysis becomes similar. Okay, just because from these band you can consider this emissivity as just some epsilon 1. Or what they do is they kind of take averages of these values. Okay, if you kind of average these values, you can just represent it as a straight line as we have done in this question. Okay, so I hope you can understand the actual, how actually this and these kind of questions are done. I mean, in the actual reality of these kind of like seemingly simple, simple problems, and how people basically use this step function to denote, uh, to denote mainly how, I mean, the step function is kind of a easier approximation because now we can take the spectral emissivity for a given band outside the integral. Basically what we did here, as I said. And then if that is done, we can easily use the definition of the band emission that we just saw at the beginning of this class. Typically, because once this emissivity is taken out, this is just the ratio of emissive powers in that band to the total emissive power of a black body. And then you can simply use the band emission function to basically calculate this fraction, given that we know the wavelength and the temperature of the body. Okay. Okay. All right. I hope this is clear. We have basically calculated. So what is this? This is nothing but your total hemispherical emissivity. All right. So once you know the total hemispherical emissivity, there is also one more part of this problem, which is to calculate the total emissive power. So how do we calculate the total emissive power? This is something that you need to tell me now. How do we calculate this ET? That is the total emissive power of this real surface. Yes? Any idea? Just use the definition of, the total hemispherical emissivity. So we just now saw, I mean, not just now, but we just saw that my total hemispherical emissivity can be defined as the total emissivity of the real surface to the total emissivity of black body. And we just need to calculate this. And we know all these things. This is known and this is known. Which means my total emissivity, or the total hemispherical emissive power to be precise. Yes, exactly. The total emissivity times sigma times TB raised to the power 4. Exactly. That's what you need to do basically. Okay. So the total hemispherical emissive power, this ET, is nothing but the total hemispherical emissivity multiplied by the emissive power of a black body, which is EB times T. And as you have rightly pointed out, this hemispherical emissive power is the hemispherical emissivity, which we just now calculated, which is 0.558, 0.558 multiplied by sigma, which is 5.67 into 10 to the power 8 into the fourth power of its temperature. Sorry, this is minus a into the fourth power of its temperature. The temperature was 1600 Kelvin, so it becomes 1600 to the power 4. Typically, because this EBT, that is the emissive power of a black body, is nothing but sigma times T surface raised to the power 4, or TB raised to the power 4. Okay, so if you calculate this, the total hemispherical emissive power simply turns out to be around 207 kilowatt per meter square, because of course the emissive power is a flux, so it will be watt per meter square or kilowatt per meter square. So you can verify it at your end. This is the answer that you should get, when you calculate the total hemispherical emissive power of this real surface. So I hope now you can understand what basically we did. So I'll repeat the problem. This is an important problem, and similar problems are there in your assignments, and I hope this problem will kind of give you a guide to basically how to solve those assignment problems. So it says that, if you remember, it says that it was a diffuse surface given my variation of spectral emissivity with respect to the wavelength. Our task is to calculate what is the total hemispherical emissivity and thus the total emissive power. Okay, so we took the so we started so what we did, so since we are given the spectral emissivity, we started from the very definition of spectral emissivity. Okay, which is basically this. Okay, correct, that we started from the definition of total emissivity itself, and then related the spectral emissivity from the definition of how my total properties are related to the spectral properties. Okay, and once we did this, okay, we basically used the fact that my spectral emissivity in the band of 0 to lambda 1 and the spectral emissivity in the band from lambda 1 to lambda 2 are just some constants. So we took these integrants, these integrants, that is epsilon lambda 1 and epsilon lambda 2 outside the integral, and then we just end up getting a fraction of the emissive power in between the wavelength 0 to lambda 1 and the fraction of emissive power in between the wavelength lambda 1 to lambda 2, and that we have represented this in terms of the band emission function that we just defined at the beginning of the class. Okay. Now, once we define the band emission function, we are still left to do one thing, because we know that these band emission functions are only a functions, they just give data from 0 to a particular wavelength lambda. So for this lambda 1 to lambda 2, we just use the principle of integration to basically write this as 0 to lambda 2 minus 0 to lambda 1. This is just the basic principle of integration that again we saw in the discussions of band emission function. So once this is done, everything is known, because these functions can easily be evaluated once we know the product of, let's say, lambda times T. For instance, if we want to evaluate this, we just need to know what is lambda times temperature. Once this is known, these functions are readily available in the table that we just saw. Okay, and then we know these functions, these emissivities are known from this data itself. Okay, and then we just evaluated what will be the total, hemispherical emissivity. And once you know the total hemispherical emissivity, you can calculate the total emissive power of the body, typically because you know what is the emissive power of a black body, which is basically the definition of the total emissivity of a real surface. Okay. So in that way, we basically use this definition to calculate what is ET, which comes out to be around 207 kilowatt per meter square. All right, guys. So this is the problem. I understand this is a little bit involved problem, but yeah, this will basically help you to solve, not only solve, but have a good understanding of what do you mean by spectral properties, and how to use the band emission tables to basically calculate the spectral properties or the total properties, and vice versa. So sometimes you may get the total properties and you might be asked to calculate the spectral properties or the function of the band emission value, and the vice versa. So these things should be clear to you, how they operate, and then you can calculate anything, whatever you are asked to do. So okay. Yeah. All right. So we will not solve any numerical now, because we don't have enough time yet, but we will discuss something. So we'll briefly discuss the Kirchhoff's law and for gray bodies. So I'll not prove the Kirchhoff's law. You have done basically this in the class, but before that, I'll stop here for some time. If you have any questions, you can ask. You feel free to ask me. Feel free to bring out your questions. All right. If no questions, we will, just see the claims of Kirchhoff's law, because this is something that I said it in the last class, that we will see this Kirchhoff's law. So what Kirchhoff's law says is that the most fundamental definition of Kirchhoff's law to me is this, that spectral, the spectral directional emissivity of a body, which is, of course, it's, since I'm saying it's a spectral a spectral directional emissivity, meaning that this epsilon is a function of lambda, it's a function of theta, it's a function of phi, and of course it's a function of temperature. And this is equal to the spectral, the spectral absorptivity. And since I'm saying it's spectral, it is again a function of, lambda, it's a function of theta, it's a function of phi, of course it's also a function of temperature. Okay. So to me, this is the most, actually, it's not required to write the temperature here, because of course when you're evaluating this, you're evaluating at the same corresponding temperature only. So you can just write it as lambda, theta, and phi to be precise. Okay. But anyways, this is the most fundamental definition of the Kirchhoff's law. Okay, which says that your spectral, directional emissivity is equal to the spectral, directional absorptivity. Okay. And remember this equation that I wrote, or this I mean, whatever you say, it's a equality or an equation, whatever I wrote, this is always applicable. And that's why I say it's the most fundamental definition of Kirchhoff's law, because it is always applicable. I mean, always applicable, because this epsilon lambda theta and alpha lambda theta are inherent surface properties. So, which means that I don't need to bother about the directionality or the spectrality or like assumptions that it's a gray body and things like that. Okay, it is. So remember, these, I mean, this epsilon lambda theta or this alpha lambda theta, these are just the property of a surface, because I have not provided any restriction to the fact that it's a gray body or it's a diffuse body and so long as things like that. Okay, so this form of Kirchhoff's law uh, is, as I say, the most fundamental form of Kirchhoff's law, and it just says that your the spectral directional emissivity is equal to the spectral directional absorptivity, and always start from these. So if you are asked the Kirchhoff's law, to me you should state these definition, because this is independent of any assumptions that comes into the picture. Now, for instance, if I say that I have something which is known as a diffuse body, then you can simply write that your epsilon lambda you know is just my alpha lambda. Typically, because I now have a diffuse body. This is one assumption that we have just considered. Okay. So as I said, this is the most fundamental form of the Kirchhoff's law. Okay. Yeah. Why not temperature dependent? Actually, it's temperature dependent. But the thing is, I'll tell you actually why it's not. It is, so it's not that they are not functions of temperature. They are functions of temperature. I'm just I'm just stating it that when you are, let's say, when you're evaluating this, let's say, emissivity. So in general, when you write this spectral directional emissivity, you will write it as the intensity of radiation for a real body at the temperature to the intensity of radiation of a black body at the same temperature. Okay, so it's like when you evaluate these radiation properties, you are calculating the radiation properties of the real body with respect to the radiation properties of the black body at the same temperature itself. And that's why implicitly it is not always necessary to write the T. Okay, because it is taken for granted that when you are comparing properties, okay, for real surfaces, you are comparing with black bodies at the same particular temperature. Okay, and that's why it is sometimes not so customary to bring the T into the picture. But it is not wrong if you just put a T here. It is not wrong actually. Okay, but since you are comparing real bodies with black bodies at the same temperature, that is, if you compare the properties of, let's say, if you compare the intensity of radiation of a real body, let's say at 2000 Kelvin, you need to consider the intensity of radiation of the same black body at 2000 Kelvin itself. And that's why sometimes you don't write radiation properties as a function of temperature, but inherently it means that you are calculating the properties at the same temperature only. I mean, you are calculating the properties of the real body in the same temperature as that of a black body itself. I mean, is it clear? Or okay, here it's not the same wavelength. I mean, here see. So if you are writing this, okay, that means you are calculating it at a particular wavelength and at a particular direction. Okay. So again, as I said, that if you are calculating this ratio, that is epsilon lambda theta, okay, so you need to consider this I lambda E of a real body to the IB lambda, which is for a black body at the same wavelength itself. Yes, essentially, yeah. I mean, essentially, you should write the temperature in that context also, because see, when you are comparing wavelengths, also you are also comparing this with respect to the same wavelength. So I think yes, in that context, I mean, it makes sense if you write temperature. Okay, so in some books they don't write the temperature; they just write this thing. But I think it is more accurate, as you have rightly pointed out. You should write the temperature there, because see, if you are comparing, let's say, the spectral properties, you also need to compare the same. I mean, you also need to compare the property of the real body with respect to the black body at the same wavelength itself as well. So I think yes, that is true. You need to also you know you are also evaluating it at the same wavelength. So I think it's correct if you bring the temperature here. Okay. Yeah. So yeah, it's correct. So I mean, it is good, and it is more fundamental if you write temperature. I mean, so it was. So I was thinking it's in some other direction, so that's why I removed the temperature. But it's true. You need to write the temperature also. Okay, so I think we're clear on this, and thank you very much for bringing this point out. Uh, but yeah, so is it clear? Because we are drawing comparison. Yes, exactly. See, if we are drawing comparison, we are basically comparing. We should always compare apples and apples. Okay, we cannot just compare apples and oranges. So I think it is true that we should bring. So in general, we should write the temperature there. Okay, all right. So thank you very much. So now, as I said, this is the most fundamental definition of Kirchhoff's law because these are just surface properties because you are evaluating this at a particular wavelength, at a particular direction, and at a particular temperature. Okay, so this means these are just a mere surface properties, and that's why this form of Kirchhoff's law is the most fundamental form. Okay, and then if I assume it's a diffuse body, this means that my properties are now not a function of direction, and I can simply write it down as you know. So yeah, so as you have pointed out, it's better to write it down as something like this. For a diffuse body, it is epsilon, which will now be a function of lambda and t, and this is alpha, which will now be a function of lambda and t, and this is true for a diffuse body. Okay, and if I now say that I have something which is known as a gray body, which means that my properties are independent of wavelength, then I can say that my epsilon t is equal to alpha t, and this is true for a gray body. Okay, so it's sometimes called a gray surface or a gray body. All right, so these are the multiple forms of Kirchhoff's law, and you need to understand how these forms are basically how these forms are basically coming from by taking the inherent assumptions. For instance, if I can say that if I have a diffuse and a gray body, I can simply write it as epsilon t is equal to alpha t, which is my total, which is my total emissive, sorry, the total emissivity the total hemispherical emissivity is equal to the total hemispherical absorptivity. Of course, that is true for a gray body and a gray and a diffuse body. But this, so when you solve problems involving the Kirchhoff's law, so if you ask me, I prefer to use this form and then go into the subsequent form depending on the nature of the problem or the assumptions in the problem that are given. Okay. So I hope, so again, I have not derived this. I have not shown you the derivation, but it is there in the lecture series. Please, see the lecture series to understand how these derivations come from, because in problem solving session it is not possible to show you the derivations, but these derivations are equally important to the problems that we see, because essentially the problems can be solved once your theory is clear on these perspectives. Okay, and that's why these things are important. But yeah, but of course, like these things, like how these things come from, it is available in the lecture series, and please have a look at your free time, because they are just the recordings of the classes basically. Okay, so I'll not stretch the discussions today. We'll end the discussion here. So we basically saw something which is known as the band emission function. We then moved into the most fundamental property of real surfaces, which is emissivity. We saw what is total hemispherical emissivity. We saw basically what are spectral emissivities. We saw something which is known as directional spectral emissivity. Solved the problem involving the band emission function and emissivity. And then we saw, after the problem, we ended our discussion with something which is known as the Kirchhoff's law and gray bodies, and then so what is the form of Kirchhoff's law and what different forms of Kirchhoff's law are. Okay, with respect to the concept of diffuse and gray bodies and things like that. Okay, so I'll end the discussion here and we'll proceed. So there is one problem. Essentially, this problem is similar to the problem that we already solved. Okay, so I'll not discuss this problem now because we don't have enough time to solve this problem. But you can try this problem out. You can try this problem. Okay. Again, I have taken this problem from the book of Ingropera. That is the reference. So you can I think it's in the first chapter of radiation. So you can see this problem. It's an example problem. So you can see this problem at your end, and maybe before starting the discussions of the next class, I will briefly go through this problem once and how to basically calculate the things that are asked in this problem. Okay, but having said that, I'll stop here for today. We'll not solve this problem now because we don't have that much amount of time to solve this problem. If you have any doubts or if you want to have any discussions on these topics, you are feel free to let me know. And also, like, if you have any subsequent doubts, you can ask in the discussion forum of the website. I mean, in the website. Okay, I'll stop here. And if you have any questions, you can ask me, or else we'll meet in the next class. Okay, all right. So if no questions, thank you very much, guys, for attending this session. Uh, we'll meet in the next week. Thank you very much.